Hello, and welcome to the Data Science Institute's virtual seminar series. My name is Dr. Leno da Silva, and I'm a Data Science Ambassador at the Lawrence Livermore National Laboratory. Data science is essential to many of the lab's key program areas. With the help of some of the world's most advanced supercomputers, we work in a variety of fields and application domains. Through basic and applied research, our data scientists are working to solve some of the world's most pressing challenges, in areas ranging from precision medicine and advanced manufacturing to energy and national security. Here at the lab, the Data Science Institute acts as a hub for data science activities, including this seminar series and other events to introduce new ideas and encourage collaboration. Speakers from other institutions are invited to share their innovative approaches with our data science community. With recordings of these seminars, like the one you are about to watch, we are reaching a wider audience than ever before. So, welcome! If you have questions or want to follow up after the presentation, check us out online at data-science.llnl.gov or send us an email at dsi-seminars@llnl.gov. Now, sit back, relax, and enjoy the seminar. Let me introduce our speaker, Hemant Kola. He is a principal member of the technical staff in the Scalable Modeling and Analysis Department at Sandia, which means he is our neighbor, so there is no excuse to not collaborate with him. It's as hard as it is to collaborate with anybody here at the lab because it's like very close. He obtained a bachelor's in aerospace from IIT Madras and a master's in the same topic from the Indian Institute of Science in Bangalore. His PhD is from the University of Cambridge. His interests lie in the intersection of high-performance scientific computing and statistical learning. He's currently working on projects involving tensor decomposition for various analyses, and he has worked with a lot of different things, including modeling and direct numerical simulation of turbulent combustion, in situ scientific data compression, and asynchronous many-task programming models for HPC. So I'm gonna let our speaker talk for himself about his work. So thank you for coming. Let's start your talk now.
Thank you, Leno. Thanks to everybody who's attending both in person and remotely. Hopefully I'm audible, but if my voice is not coming through, just please interrupt, let me know. I'd also like to thank Pyra for helping with the arrangements and the Data Science Institute. It's a nice opportunity to just cross East Avenue and then come in person. I've been working at Sandia for 13 years, and we crossed the Rubicon so to speak. But as Leno mentioned, I'm a staff in Sandia National Labs. I work at the intersection, as most people do, of many different topics. But today I'm going to present some work we've been doing on leveraging higher-order multivariate statistics, specifically for some targeted analysis of scientific data. So I'd like to start by mentioning a few acknowledgements. Funding, of course. A lot of the work that I'm presenting has been funded by DOE Oscar, Advanced Scientific Computing Research. The Exascale Computing Project, which is actually a fairly large umbrella of projects, but within ECP, two projects that I've been associated with, XLN and Conversion Relay, and also the LDRD program at Sandia. Also, many collaborators. I've had the privilege to work with a lot of excellent collaborators, both at Sandia and Australian institutions. It's too many to go through, but yeah, here's an incomplete list. When Leno first sent me the invitation, I was mentally prepared to present a talk on the first topic that I'm interested in, which is tensor decompositions. So tensor decompositions or tensor factorizations are these two graphics illustrated, are essentially higher-order extensions of matrix factorizations, and they have many applications for scientific data analysis. But this topic was the subject of a recent seminar. I believe Joyce Ho was the speaker. So I mentioned this to Leno, and he said it's probably not ideal. But then I thought I'd give a talk on a second topic that's of interest to me, which is uncertainty quantification for PDE systems. Specifically, for a UQ of PDE systems, there's many different approaches. The one particular approach that we are interested in is this approach called solving PDF equations. Essentially, if you have any PDF system with a certain right-hand side that parameterizes the physics through some parameters lambda that are uncertain, and you want to propagate that uncertainty through, that whole setting implies an exact equation for the PDF of the state. So from the uncertain PDF system, you can derive an exact equation for the joint PDF of the state. This equation is exact, but it's difficult to solve, and that's where research comes in. I mentioned these two topics because anybody is interested, if this resonates with any of you, and I'll be grateful if we can have a conversation offline or sometime later. But yeah, my talk today is not going to be on either of those. It's going to be on using higher order statistics. So I'd like to start by, so this is the outline. I'll start with just giving a few minutes of background on scientific computing. I recognize that data science means different things to different people. So I want to kind of set the stage and describe the domain within which we do data science. Then I'll motivate the use of higher order joint statistics, followed by two concrete applications that we have sort of put higher order statistics to use. And then finally, because we are working within distributed HPC, we have to pay attention to algorithms that map well to HPC resources. So that requires designing of scalable algorithms. I'll close with it. All right. When I say scientific computing, primarily I'm referring to kind of scientific investigations that are looking at complex systems in high fidelity. So a few examples here. On the left is the domain that I'm most familiar with, which is turbulent reacting flows. So this is an example of a simulation of a fuel jet that is turbulent, and it would ignite under certain conditions, and this represents sort of conditions within an internal combustion engine. It's a fairly complex system, requires a lot of computing resources to study. Another example is, as the picture suggests, energy systems, so turbulent flow past like a wind turbine. And the third example, obviously, is also something that we're all familiar with, Earth systems. Specifically, in this case, this is a plot of ozone from a simulation of the atmosphere. So these are some examples. Obviously, they do not represent the entire spectrum of scientific computing, but these are some examples that I'm familiar with. And these are all fairly complex systems requiring very expensive simulations that generate a lot. Why are these simulations expensive? I'd like to use the example of turbulent flows to kind of convey the multi-scale nature of these systems. So in turbulent flows, there's a classical theory that establishes this concept called the kinetic energy spectrum. So you're typically solving a PDE system, Navier-Stokes, essentially, and depending on the physics in the flow, you may have diffusion and chemical reactions. But the flow itself has an energy spectrum. By that, what I mean is, if you plot the logarithm of kinetic energy against the log of wave number, which is the inverse of the length scale, classical theory suggests that the energy is spread over a certain range of length scale. And there is a universality to this energy spectrum. The theory suggests that there's a slope that is minus 5 plus. But essentially, this tells you, and the width of this spectrum is related to the Reynolds number. So Reynolds number essentially is a measure of how turbulent the flow is. Another thing is, if you needed to resolve in a simulation all of these scales, then you are dealing with a length scale ratio, which is the largest length scale, which is a small wave number, the smallest length scale, which is the large wave number. That ratio goes as Reynolds number to the 3/4. Likewise, time scales go as Reynolds number to the half. So the total degrees of freedom you are having to deal with goes as Reynolds number to 11/4, which gets very expensive very quickly. So how are these dealt with in a computational setting? There's broadly two classes of approaches. The first, of course, is just brute force resolve everything. Right? This is true high fidelity. So you pay the cost of this extreme number of degrees of freedom. So that's known as direct numerical simulation. So you you end up with really large simulations of large data sets. A way to mitigate the cost is to recognize the universality of this energy spectrum, so the universality of the dynamics below a certain scale. And you can model the statistics. In the extreme, you can essentially resolve only the coarsest length scales and model everything else. That's one extreme. An interim approach is to model only the fine scales and resolve the coarse. But the point is, whether you're doing the high fidelity DNS approach or some of the coarse resolved approaches, you either are having to deal with large data sets and trying to glean information and insight from them, or provide statistical models that represent the statistics of the flow. So in either case, there is a plethora of data science problems that need to be addressed. So here's a list, again, an incomplete list, for me at least motivated by the requirements for something like turbulent flows or turbulent flows of reactions. There's, again, I'm not going to go in detail for all of this, but these simulations, by their very nature, require a whole lot of data science to address these challenges reliably. And what makes these data science requirements challenging are, again, many aspects. Some of them, like I said, a broad range of scales, which means you have to have statistical representations that are accurate over a wide range of scales. The dimensionality of the state space is fairly large, and so on and so forth. Anyway, for this talk, I'm going to focus specifically on one challenge, which is many of these systems, by their very nature, are governed by non-Gaussian statistics, non-Gaussian multivariate statistics. So that's an aspect that's not paid enough attention to, in my view at least, and that's what motivated some of our questions. All right, hopefully I've kind of set the stage for looking at higher order statistics in scientific data sets. I'm going to motivate that a little more concretely in the next few slides. So why do I say that looking at higher order statistics is important? So let me start with, if you did a quick survey of the vast number of data science techniques that are used, you will probably conclude that a recurring theme is essentially concepts or techniques that are centered on second order statistics. By second order, I mean covariance relation. So here's a list again, just reporting or observing or examining correlations, analysis of variance, Sobol indices, Kalman filters, principal component analysis and its equivalent technique, single value decomposition. All of these, in some way or another, are related to second order statistics. To assume that second order statistics based techniques are sufficient or adequate, you're implicitly making an assumption that Gaussian statistics apply in the system you're looking at. But we know that that's not the case for many, if not all, scientific phenomena. In turbulence, at least, there are many settings where the distributions of interest are non-Gaussian. So beta distribution is actually quite common in turbulent flows with scalars that are being transported. Log normal distribution is quite common. And in all of these settings, every time you're dealing with a non-Gaussian distribution, higher order statistics have important information. So if you're stopping at second order statistics, you're not gleaning more information that you should. So let me illustrate this with a synthetic data set. What I'm plotting here is just a bivariate synthetic Gaussian data set that I've rotated. This is the classical illustration for principal component analysis, right? From this data set, if you were to perform PCA, then your PCA vectors would align with most of the spread of the data. So the first solid vector here is the first eigenvector of the covariance matrix from this data set. It would align with where most of the data is spread. The second vector is by construction of problem. So this is what PCA would give you. So in some sense, these vectors are capturing the covariance information. Now, for this data set, if I added a few sample points, that are kind of far away from the main cluster. Now, this entire data set is no longer joint normal. And from this, if you computed the covariance eigenvectors, they remain roughly the same. They do not budge. But if I instead, from this data set, computed what I'm calling the cokurtosis tensor and factorize the cokurtosis tensor. So let me define what I mean by cokurtosis. So cokurtosis is, for this talk at least, it's the fourth order joint cumulant. So if you had a vector of zero mean random variables, then a cumulant is essentially, E here is the expectation operation. It's the joint fourth order moment minus interaction of the covariance. So this is the joint fourth order cumulant. This is what I'm calling as the cokurtosis tensor. I don't want to point out that if you did a search for the term cokurtosis, you will find a lot of literature from the finance modeling domain. Apparently, it's been widely used there. That's where all the money is, of course. But they define cokurtosis simply as the joint moment. I'm defining cokurtosis as the joint moment. All right. So from this data set, I've computed the cokurtosis tensor. Since it's a bivariate data set, the cokurtosis tensor is 2 by 2 by 2 by 2. And I factorized. Once I factorized it, the first principal vector, which I'm calling the principal cokurtosis vector, now you can see does actually track the outlier points. If I move the outlier points around, the PCA vectors or the covariance vectors are insensitive, but the cokurtosis vectors are. This is a visual illustration of fairly obvious and intuitive concepts. The more you have information in the tail end of a distribution, the more relevant the higher order moments and cumulants become. This is really just an illustration. So I've said I've factorized this tensor. How did I do that? So this brings me to my kind of first digression. Higher order statistics are higher order tensors. So covariance is an order 2 tensor, meaning it's a matrix. Coskewness would be an order 3 tensor. Cokurtosis is an order 4 tensor. Moreover, they are symmetric tensors. By that, what I mean is the entries of the tensor are invariant to a permutation of the indices. So the element ijkl is the same as jikl and so on and so forth. So to deal or grapple with higher order statistics, you end up essentially in tensor factorization or tensor decomposition. So factorizing the cokurtosis tensor or any higher order moment or cumulant tensor is essentially a problem of factorizing a symmetric tensor. There are many techniques for factorizing higher order tensors, and they all have special forms for symmetric tensors. So one example is, again, this was mentioned in the one of the previous seminars, Joyce was seminars, tensor decompositions, is called canonical polyadic. So essentially, using an order 3 tensor as an example, what this decomposition does is it factorizes an input tensor as sum of rank 1 tensor. So each rank 1 tensor is essentially an outer product of vectors. Now, the symmetry of the tensor ensures that in each rank 1 set, the vectors are all the same. In general, if the tensor is not symmetric, these vectors are not. And then R here is the rank. So you choose how many components, how many such components you want to approximate. There are certain ambiguities with CP decomposition. The choice of rank is not straightforward. It's actually the optimal rank is an NP-hard problem. That's another topic. These vectors, so Q1, Q2, and QR are not necessarily orthogonal, which, depending on your objective, may be better. Or you may want orthogonality for some other reason. Another example of tensor decomposition, which also can be specialized for symmetric tensors, is higher order SPD. There is a very nice paper from 2000 that establishes higher order SPD as a proper generalization of matrix SPD. If anybody is interested, I highly recommend reading this paper. But in higher order SPD, again, you are essentially representing a higher order tensor as a set of factor matrices. Each factor matrix is an orthonormal basis along that space, multiplied by what is known as a cotensor that represents the multidimensional or multi-ring arrangement. In general, if tensor was an order 2, meaning a matrix, then this would be an SVD. So you would have two factor matrices, which are the classical U and V orthonormal matrices, and the core just becomes diagonal, which is a singular value. But if you go for dimensions more than 2, then the core is not diagonal, it's actually a tensor. For a symmetric variant, meaning if your input tensor is symmetric, so no matter which way you rotate it, it's the same. All of these factor matrices end up being. So you can just unfold this input tensor along any of the modes. The unfolding would be the same, and you can just do SVD. So in our work, we chose higher order SVD to factorize the cokurtosis concept. For its simplicity and ease of implementation, it was really a convenient choice. I do believe that there are settings where CP probably is, this sort of a decomposition is probably a better choice, but for the time being, we have stuck with this. There's another approach, which is called tensor eigenpairs. So for any order D symmetric tensor, you can define an eigenpair, meaning a scalar lambda and a vector x, which satisfy this relationship. So the tensor times the vector raised to the power d minus 1 is equal to 1. So again, this is a higher order extension of just the matrix eigen decom. This is another option. We haven't, again, as I said, explored this, but the point is there are different ways, as it is with matrices, with tensors, there are many different ways of factorizing them. So the choice depends on what you're up to. All right, so I've kind of given a flavor for what can be done using information from higher order statistics. So let me take that forward to two concrete examples of how we put them to use. I do want to mention that, throughout this work, I've been kind of a student of statistics rather than an expert. So we haven't done any contributions in terms of like foundational theory and so on. We adopted a more utilitarian approach, which is take these concepts and see how quickly we can put them. So the first use of higher order statistics that we found, again, from the visual should be obvious, is rare event detection. Let me define the problem. I'm dealing here with what I call rare event detection. So it's different from anomaly detection as it is classically described in literature. So anomaly detection usually deals with identifying individual samples that are spurious, that are wrong, that somehow do not belong, right? But for scientific computing, we're dealing with a different problem. We are interested in detection of rare events. So these are events that are not unphysical, they are physically valid, and they're not an individual sample. Usually these events are defined by a set of sample collections. And often there's an interest in detecting them as early and as precisely as we can. So again, going back to the combustion example, as I mentioned, this sort of simulation is where you're injecting a fuel and it would ignite at some point. The turbulent flow makes it hard to determine when and where it would ignite. But during the course of simulation, you would want to be able to detect it as early as possible. How is it currently done? For combustion, at least, a combustion scientist would come and say, okay, given the fuel chemistry, given the conditions, the temperature and pressure and so on, I know that if certain intermediate species cross a certain threshold, and also if temperature crosses the threshold, then my domain intuition tells me that that's an ignition event. So currently, identification of ignition kernels is based on ad hoc thresholds, and it's heavily supervised. So if you change the fuel chemistry or if you change the conditions like temperature and pressure, these thresholds would not work. So the identification of these rare events is not generalized. So we can apply sort of, again, classical anomaly detection type ideas. There are ideas based on clustering and finding samples that are far away from a cluster and so on. But many of those are related to essentially some distance-based metric in a feature space. For combustion, at least, the feature space is fairly large. We are often dealing with simulations where there's like hundreds of species, 10 species in the system. So in high dimensional setting, distances start to lose their meaning very quickly. So classical anomaly detection approaches probably will not work very well. So obviously, we wanted to leverage the higher order statistical information. So the solution that we proposed, and I'm illustrating it here visually. So imagine if your simulation is kind of divided into subdomains, which it usually is for distributed computing. Your spatial domain is decomposed, and each subdomain is shipped off to one processor, one node. Now imagine that all of your subdomains represent what is most of the subdomains represent some kind of a nominal distribution, but the one subdomain that has kind of a different distribution is the one that has a rare. So all of the other subdomains represent something that's regular or normal. Note here that I'm not stipulating that there are no outliers. It's just that the subdomain of interest has outliers in a manner that's distinct from everything else. So essentially, we want to leverage the information in the higher order joint moment, like I said in cokurtosis, and identify them. So as you can see, this particular subdomain has the cokurtosis vectors or principal kurtosis vectors orientation that is distinct from everybody else. So can we leverage that principle essentially? Although I'm showing this here for distributed computing, I'd like to point out that this applies just as well to federated learning. So in federated learning, you have data distributed at different sites. You want to be able to learn something without actually having to gather or exchange the raw data itself. And this sort of an approach applies perfectly to a federated learning setting. But a lot of analysis techniques in distributed computing would apply to federated learning almost off the shelf. This can also be applied to time series data. So if you can imagine each of these boxes aligned along a time axis, where each of them represents some time window, then you can do rare event detection in a time series data. Anyway, so how did we formalize essentially the concept of leveraging information in higher order statistics? So the first step is we need to factorize a cokurtosis tensor in each subdomain. So factorization would give us a set of principal values and principal vectors of the cokurtosis tensor. Now, I don't want to just compare the set of vectors and values. I want to distill that information further. So to that end, we've proposed a definition called a feature moment metric. So essentially, if you have two features, then for each feature, you can assign a metric of kurtosis. So in this case, the feature kurtosis metric. The way we've defined it is for any feature I, so in this case, I is 1 and 2. For any feature I, you can compute the dot product of the set of all principal kurtosis vectors with that basis vector of that feature and weigh it by the singular value and then divide by the sum of singular value. Anyway, the point of all of this is when so defined for any data set, the sum of all feature moment metrics becomes unity. So the interpretation then is each feature moment metric essentially tells you what portion of the moment, in this case the kurtosis in the data set, can be attributed to that feature. What do I mean by that? So in this case, the outlier data set, the outlier samples are roughly at a 45-degree angle. So the outlierness in this data set roughly comes from both the feature 1 and feature 2. So the feature moment metric is roughly half and half. In this case, most of the outlierness is, as you can see, aligned along the first feature. So the feature moment metric for the first feature comes out to be like 0.99. The second one is 0.1. So essentially, the feature moment metric tells you roughly what fraction of the metric, what fraction of the moment is attributable to each individual feature. The second nice property is that since they sum to unity in any domain or subdomain or data set, the feature moment metrics by construction sum to unity. So you can think of them as like a histogram or a discrete distribution. So you end up just having to compare these feature moment metrics vectors. So it's a matter of just comparing discrete distributions. So you can use any number of divergence metrics. So we used Ellinger distance, which has a nice property that it lies between 0 and 1, and it is symmetric. So essentially, identifying which subdomain is or contains a rare event is determining a Hellinger distance for that subdomain based on the feature bound metric. And once the divergence metric crosses a certain threshold, you can flag that subdomain as containing the rare element. So the reason we went through all this trouble is that all of the computation in the analysis is localized. So all of the computation is basically computing the cokurtosis tensor and factorizing it. What you need to communicate is just a small set of numbers, just a vector that's the size of the number of features. And this is what you would ideally want in any distributed computing. Right? You want to localize the computation and communicate as little as possible. How does this perform? So this whole approach was proposed in a 2019 paper. So in that paper, we also presented some analysis of the accuracy. So here I'm showing one time instead from a spatially 2D turbulent ignition simulation. So there's a simulation where an ignited fuel is kind of mixed with air, and the simulation just evolves. It's a doubly periodic domain. So at some point when the conditions are right, locally the fuel would ignite and you would have local ignition hotspot. So that's what's visible from the plot of heat release rate. So heat release rate is a measure of the exothermicity of the fuel. This domain was divided into a 12 by 12 partition, so like 144 subdomains, each subdomain mapped to one processor or RAM. Based on combustion domain knowledge, if heat release rate crosses a certain threshold, then you can denote that particular partition as having an ignition current. So based on that, we have a ground truth map that comes out to be like this. So these partitions are the ones that can be classified as having the ignition event. Our kurtosis-based anomaly detection or rare event detection flags these partitions. So it's not 100% accurate. There is one false negative, so it misses this partition, and there's one false positive. So, and also remember, there's two thresholds here. There's a threshold that establishes the ground truth, and there's an anomaly metric threshold based on the Hellinger distance that we use to classify each partition. So in general, for a more systematic analysis of the accuracy of these kind of techniques, there's an approach or a concept called ROC curve. An ROC curve, or receiver operating characteristic curve, lets you quantify the accuracy of or the performance of a binary classifier. So if you have a binary classifier that's governed by a certain threshold, then as you vary the threshold, what is the true positive rate or the false positive rate of that binary classifier? So any one curve essentially represents the sweep of that accuracy of the classifier as you vary the threshold. In our case, we also have a threshold that determines the ground truth. So we performed the sweep for 3 different ground truth thresholds. The point is, any classifier that's worth its salt, if it's better than a random guess would just be a 45 degrees, right? Roughly every other decision is either a true positive or false positive. So if your method is better, then it needs to lie above this 45 degree line. The farther away, the better. So our conclusion is that across different thresholds, the method does actually perform fairly well by this characterization using the Alex method. I presented all of this for distributed computing, but subsequent to that paper, we realized that we could, as I mentioned, apply this to different settings. So this is a time series data set. It's completely different setting. It's not distributed computing. It's rather observational data. So there was an effort at Sandia where biofuel synthesis using algae ponds was conducted. What happens is you have these ponds where you feed the pond with something that lets you cultivate, or it will produce algae, and then you can cultivate that later from synthetic biofuels. But occasionally, some contamination causes the ponds to crash. So the species that you want gets consumed. So to detect this, they collect samples from the pond, water samples, and do genome sequencing. And then they, based on the taxonomy, they featureize the genome sequencing. So we applied this for a fairly crude or coarse featureization. Essentially, the entire genome sequence bundled into 2 features: a producer feature and a contaminant feature. And there was one sample, one per day, and we applied this. And essentially what you can see is the point at which the producer starts to decrease and the contaminant starts to increase, meaning the inception of the pond crash, the anomaly metric does actually shoot up. So this was kind of a promising application of the technique to a setting that was not distributed computing. And motivated by this, the PI of this project actually subsequently proposed this for another problem, which is detecting disease outbreaks from individual variable data. So that's an ongoing area. But I just wanted to give you a flavor for where all this is potentially applicable. I do want to take another digression. I've been talking of use of higher order statistics, but there's an interesting connection between higher order statistics, especially cokurtosis, and this approach called independent component analysis. So ICA is also known as blind source separation or a cocktail party problem. So the idea being, imagine that there's a cocktail party and people are just milling about and talking to each other. You have a few microphones placed in the room and you collect the audio signals. From those just audio signals, you're blind, you don't see who's talking what. Can you separate out the audio signals into the individual sources? The assumption being that the individual source signals are all statistically independent. So mathematically, ICA essentially says, can I separate a set of observed variables, random variables, into a linear mixture of statistically independent source variables? So the key here is that you're mandating that the source variables be statistically independent, which is arguably a stronger condition than PCA, which seeks a set of latent variables that are just uncorrelated. So yeah, the problem is you have X as the observed random variables, which are a result of mixing matrix applied to a set of independent source variables that are statistically independent. There are many ways to solve this problem that have been proposed, but one approach essentially says the mixing matrix or its inverse, essentially the rows of that inverse of the mixing matrix can be estimated if they are stipulated to maximize the non-Gaussianity of the observed random variable. And so that in turn translates to a problem of diagonalizing the cokurtosis tensor. Anyway, so there's an interesting connection between factorizing or diagonalizing the cokurtosis tensor and ICS. So I just wanted to mention that. All right, so that first application was rare event detection. Another application of higher order statistics that we are currently still working on is dimensionality reduction. Again, going back to the combustion setting, PCA is widely used for dimensionality reduction, you know that. Within combustion, there's been a push to apply PCA for a very specific purpose. So typically what you do in combustion is you're solving a high dimensional PDA system. So the solution variables are momentum, energy, and a whole bunch of chemical species that often run into hundreds. So fairly complex hydrocarbon fuels have hundreds of chemicals. So the system is fairly large. So one approach that's been proposed is, can we run a bunch of inexpensive high fidelity simulations for the full system, like spatially zero-day simulations, collect training data, perform PCA, so that's visually shown here. Again, if you had a 2D data set, perform PCA and do a dimensionality reduction, meaning project to just one feature. So essentially, this represents the PCA projection, right? So P is your original state, and Q are some truncated eigenbases of the covariance matrix, and this represents the PCA projection. So once you do that, your eta are much fewer in number than P, and so when you substitute this in the original PDE system, you can derive a PDE set for a far fewer number of principal components. So this is being widely studied combustion literature. Our contention is that, again, if you look at this picture, in this data set, the PCA vectors align with the variance. But we contend that for stiff systems, it's not the variance that we should be seeking. Rather, the stiff dynamics are better represented by samples that are far out. So you should, in fact, look for directions that represent the higher moment. So essentially, we said, okay, instead of Q being the truncated base of the covariance matrix, let Q be the truncated matrix from factorizing the cokurtosis. So what this effectively means is PCA essentially gives you a projection that is optimal in a two-norm sense, whereas when we substitute Q with factors of cokurtosis tensor, our intuition is that this is an optimality in a different norm, not in a two-norm. I say that with an asterisk because we haven't proved that mathematically, but that's it. How does this work? So we did just a preliminary a priori assessment where we are just simply assessing the error or the loss of accuracy through just the projection, right? PCA lets you project using the covariance matrix eigenvectors, and we are proposing cokurtosis tensor. So once you've done the projection, you can do the reconstruction. And the phi tilde here is essentially the reconstruction of the forward projection and inverting it here. So because Q is a truncated basis, there is loss of accuracy. So what conversion literature typically does is assess the accuracy in just the reconstruction. So we did the same, and we defined an error ratio here. It's just essentially a log of the error per feature. So there's about 32 chemical species and temperature. So for each feature, what is the error, reconstruction error from PCA divided by the reconstruction error from cokurtosis PCA, and we take a log of that simply because that lets the plot be plotted from 0 to positive. And the interpretation here is for any feature, if the error ratio is positive, that means the error due to PCA is higher than the error due to cokurtosis PCA. So blue means cokurtosis PCA is less error, more accurate. The point is, if you just look at the thermochemical state, for most of the species, PCA is actually better. But here again, we contend that just looking at the thermochemical state that you projected and then expanded back is not enough. What you should look at are functions of the thermochemical state, which are what are used in an a posteriori setting. So if you were to apply this, you would want to see how well the chemical reaction rates that are computed from the approximate thermochemical state, right? So we are looking now at not just phi tilde, but the chemical reaction rates are the functions of the approximate reconstructed state. So when you do that, now you see the situation kind of inverse. So for many of the features, the reaction rates come out to be less accurate with PCA and more accurate with cokurtosis. So our hypothesis, which is backed out by evidence, is when you do a projection that just maximizes the spread in the data, then the spread in the features and the accuracy of the features in a two-norm sense obviously would be most optimal. But you shouldn't stop there. You should look at other quantities that are functions of the state, which are more relevant. The conclusion here is that PCA appears to be more accurate when you just look at the two-norm of the state itself. If you looked at the accuracy for functions of the state, then that would be not enough. There's one quantity that actually represents the accumulation of all the errors, which is again Heath-Tilly's rate. It's actually a weighted sum of the individual species rates. So it's the individual species reaction rates multiplied by the formation effect. But essentially, whatever errors are in the reconstruction of phi tilde and the reaction rate function applied to that, all of that gets funded. And so I'm showing this just for one case here. In the paper, we've presented this for multiple cases. You do get better accuracy with cokurtosis. So it's an early evidence that maybe you should go beyond PCA for strict dynamical systems. All right. So those were two concrete uses of techniques based on the cokurtosis tensor. I did mention earlier that our interest is in primarily distributed HPC. So to be able to make these techniques useful, you need algorithms that are scalable, that map well onto HPC. So that has prompted us to again look at algorithm design. So let me motivate that as well. Now the cumulant tensor is essentially the fourth order moment minus covariance, terms of covariance multiplied essentially. If you were to annihilate, so think of your input data as just a matrix. R is the number of rows, which is either the number of breakpoints or time steps and so on, and the columns are the number of features. Like I said, in combustion, this would be typically 100. So most of the computation in the cumulant tensor is due to the computation of the moment tensor itself. you want to naively do it for a dth order moment, you would just do a nested for loop, right? This is very, very bad. I guarantee you, if you do this even for 20 features using a simple Python code, it will slow down your computer dramatically. So this is definitely not, it's not the way to do it. It's just not performant. So there are ways to improve upon this significantly. The first is to realize that the moment tensor as well as the cumulant tensor. So I'm just going to now focus on the moment tensor because that's where most of the computation is concentrated. So the moment tensor is symmetric, as I already mentioned before. So for a general dth order moment tensor,
good. How are you?
The full tensor has n to the d elements, n is the number of features, but the number of unique elements is just this quantity, n plus d minus 1 dd. There's an approach that recognized this and said, let's lock up the moment tensor into smaller subblocks. And then essentially, if the size of it, so in this example, the full tensor is 4 by 4 by 4, so it's a third order tensor with net size of 4. And you can divide this up into a 2 by 2 by 2 set of subblocks. So each solid subblock has a symmetric counterpart. But anyway, instead of computing the full tensor, you can just focus on computing the symmetric subblock. The point is, if you leverage symmetry, you have at a minimum an order of b factorial savings, which can again be significant. So for a fourth order tensor, it's 4 factorial. We went beyond just exploiting symmetry. We said that the manner in which you organize the computation of the moment tensor itself can be modified and refactored. So we made a few observations. So the first observation is that if your input matrix is X, then any dth order moment is essentially an average of a row-wise outer product. So this symbol here, this circle symbol is an outer product, and D represents a DV outer product. So essentially, this matrix is take each row of the input matrix, do a DV outer product of that, and just do an average. That's what the moment tensor comes out to be. And you can picture this for the case of covariance, right? If you're looking at M2, then the covariance is just X transpose times X, which falls into it. The second thing is you can speak the moment tensor in a meter-sized form. So any symmetric n to the d tensor, when you meter-size it along p modes, then it becomes a matrix with n to the p rows and the remaining part. So when you put these two together, you can essentially compute the moment tensor in a meter-sized form using two sets of what I'm calling Khaslera products. So Khaslera product is a special matrix product that essentially takes individual columns of the matrix and does a conical product. So it's essentially an output product of two corresponding columns of two matrices. So you can perform the Khaslera product p times and d minus p times, and you end up with two matrices, and you can just finally do a matrix multiplication. Anyway, it's essentially a higher order refactoring of repeated matrix multiplication. So that this does end up being better. So I'm here showing performance improvements against a reference implementation. So I mentioned symmetry before, and there was a paper that leveraged symmetry in accelerating the computational moment tensors that was in 2018. So to that symmetry, we also added the refactoring, and we performed some experiments. There's again a paper where we describe how to exploit hierarchical parallelism, and I'm showing experiments. For one example, this is again a fourth order moment tensor. The parameters of the problem are the number of rows of the input matrix, number of columns, which determines the size of the tensor. And as I said, we chunk up the computation into subblocks, so these are the size of the subblocks. But the point is, for all three parameters, as you vary them individually, the reference approach is the red curve, and the refactored approach is the blue curve. And I'm just plotting execution. The first plot is for a fixed number of rows and columns, what happens is the variable block size and so on. Across all different settings, problem sizes, the refactored approach does give significant speed up compared to the reference approach. So again, the reference approach just computes the symmetric subblocks using the nested loop naive approach. The point is, where does the speed up come from? And as with many things, accelerating kernels and computing, the crux is you get most performance when you optimize for memory accesses, and that's the same here as well. So essentially what we discovered, and we reasoned about this through complexity arguments in our paper, our refactoring basically improves memory access, which results in better compute intensity. So what I'm plotting here is, again, red is the reference implementation, blue is the refactored implementation. The solid curves are flops, and these were collected using NVProf, which is a nice profiler tool that NVIDIA provides. So solid curves are on the left, flops, and L1 cache accesses. So level 1 memory cache accesses are on the right. These are dashed curves. And so you can, for any given color, you can divide the two and you get the compute intensity of this flop. So the point is, the reference implementation has a low compute intensity, meaning for each flop, each byte that you're loading, you're doing only a few flops, whereas the refactored, you're doing many more flops. And so that dramatically improves performance. So you can see that at the peak, the gap in compute intensity is roughly an order. Anyway, that's what allows us to realize significant cost savings. Where does this all lead to? So all of this finally culminates in a milestone for an ECP project, where we were tasked with deploying a machine learning capability, in this case, rare event detection, in situ. By in situ, I mean as the simulation is running live, in a fairly large simulation. So we took all of the refactoring and implemented this in a software. And then there was a joint, so the whole ECP project was organized around what they call KPP milestones. KPP3 was a milestone that demonstrated integration across multiple projects. So in this case, this was a milestone combining combustion ECP project, an in situ analysis ECP project that was actually led out of LLM, and a team at Sanjay that was part of the Exascale project. So more concretely, we demonstrated scalable detection of ignition events in an IC engine simulation. The actual simulation actually performed a simulation of 4 jets of endodecane fuel. I'm just showing here a sample, which is just visualization of one jet and ignition events. And our rare event detection technique identifies and maps each subdomain to an anomaly matrix. So you can draw a cutoff, and you'll see that the boxes with a high anomaly metric actually do center around the ignition region. So this particular simulation was, as I said, a 4-jet IC engine simulation. The code Pele is the combustion code. It's a block structured AMR mesh. In this case, it has 6 levels of refinement, 60 billion cells. But this whole integration demonstration was run on 7,100 nodes of Frontier, which is the exascale machine, and that translates to 56,800 GPUs. And essentially, the whole analysis in situ. So I'm plotting here the fraction of time the analysis coupled to ascent takes at a fraction of the time step of each time step of the combustion simulation. So we perform the analysis every time step. And so how much burden or overhead does the analysis add to the application itself? And what I'm plotting here is the percentage of that ratio. So the orange curves are essentially the analysis performed as is without writing any stuff. So when analysis was turned on, we also wrote some diagnostics to file that add a little overhead. But even that overhead is only like 3.5%. But at its most optimal, the entire cokurtosis analysis was less than 2% of the cost of the application just run natively. So that qualified us for essentially passing the milestone. So anyway, the point is, hopefully I've shown the entire gamut of results. So conceptualizing information in higher order statistics, applying them for a specific target analysis, and then the algorithms that let you run the analysis at scale that need performance milestones. So with that, I will stop and I'll be happy to take any questions. And yeah, once again, thank you for
Thank you. So anybody has any question?
One quick question. So thank you for the talk. And I like that there's so much emphasis on computation. But I think from a statistic point of view, like for high order statistics, also I wonder what's the rough like in terms of sample complexity, like number of data points? Is that like especially let's say in the genomic example you get, like if the feature dimension let's say is higher, like more than the number of samples, like how would like this?
Yeah, so you bring up a very good point. I completely glossed over. So we got this question many times. The question is, have your higher order cumulants converge? And especially if you have a fixed samples, right? Your higher order cumulants definitely require many more samples to be converged. So our intuition there is so our intuition here is that we do not necessarily require the cokurtosis or higher order tensor to be fully converged because we are not examining each element of the tensor individually, right? So the tensor itself is not converged. It's not too problematic. Really, what we want are the factors of the tensor. So if the factors of the tensor are computed with a reasonable approximation, then that's what we are using. So our intuition is that you're not hurt significantly by the tensor itself, not by the higher order moment of cumulant not being counted. So that's another reason why we stepped away from just comparing the tensor, the moment tensor element by itself. So we do not, so in these two cases, we do not compare the tensor elements individually. We distill the information in the tensor into these factors. But yeah, that's a very good point. And we haven't done any theoretical analysis. In fact, I'm pretty sure that the higher the moment, the less accurate the moment itself would be if the samples are not accurate.
So I guess then the workaround is like a future is kind of projecting down.
Into
so
that,
you're not necessarily looking up.
Yeah. So to distill the information, basically. In this case, it's a fourth order moment, and I think these number of samples here, I think the main cloud is about 500 and the outliers are just 20. So the total data set is like 5. I remember correctly. Yeah, something of that order.
Any more questions? Run online.
Yeah.
So you mentioned about ignition detection. Do you think your approach can be applied to other problems such as atmospheric flows where we typically address gusts differently? So similar approach can be applied for the gust detection.
What detection? Gust detection.
Yeah.
So we did, not me, but somebody else has been looking at identifying kind of tornadoes. Okay. So localized rare events from our data set. I believe it can be, but I haven't really done that hands-on myself. But I believe so. Anytime you have a localized rare event that will have a signature in higher order moments, you should be able to apply. And if that's something that's interests you,
okay. I'm working on atmospheric flows, so I would be interested in exploring.
Sure. Atmospheric flows at like planetary scale or more urban?
Mesoscale.
Okay, mesoscale.
Actually, this is probably the same family that you mentioned, PLSC and Exavent. So
they're in Exavent.
Okay. There is also MREX based.
Right. Yeah, Exavent is also. So
actually there is another one, ERF. So Exavent is microscale. And ERF, that's what we are working on. That is mesoscale.
Mesoscale. Yeah. So like a continent or?
Yeah, it's like continental US, something like that, 3,000 to 4,000 kilometers.
Okay. Yeah, I'd be happy to. Curious about your application. So separately, we are applying tensor decompositions for climate systems.
Yeah, I think this will be a very good use case.
Yeah.
Any more questions? Okay. I have one question, maybe actually like stepping back to the high level motivation of doing all this work. Right in the beginning of the talk, I might have misinterpreted, but you say that like basically we can do the simulations in a way that it's like very high fidelity, but then it's like extremely slow, or you can follow the statistical approach, which is like it's going to give you something approximate, and this is kind of like what started all the work you have presented, and this idea of like using statistics to approximate things. My question would be, would it be interesting for a lot of applications to actually combine those two ways of like simulating things? So like having a multi-fidelity approach in terms of like, okay, you're gonna use your statistical way of like reasoning for most of the things. When you deem that the uncertainty is too high, or when you deem that you have found something that it looks like an anomalous example, then you run the high fidelity simulation. And like if you have thought about like doing something.
No, you're absolutely right. So the concept of using multi-fidelity approaches is very much a hot research area in different domains. So again, across different domains, like he said, mesoscale atmosphere simulations. I'm familiar with engine scale simulations, but performing multi-fidelity simulations, or some people call it coupled simulations. Essentially, what you have is you have like a high fidelity mesh and you turn on the simulation, and then at some point you decide you can just coarse and then you switch to a coarse result. But at some point, again, you would have to realize that the coarse resolution is not happening. So it is, from what I know, it is still in a conceptual state. For turbulent flows, at least, I don't know them being production ready. So many of the theoretical aspects are still being worked out. So as of now, these different fidelity approaches are still run separate. Somebody would essentially run their simulation either purely in the high fidelity approach or purely in the coarse result. But yeah, this is very much
Okay, there are some people here in the lab working with mesh refinement, which I don't know like how similar to your specific application it is, but a lot of like different approaches to do this kind of like multi-fidelity optimization has been tried. I'm not sure how much.
So the final simulation that I showed actually is mesh refined. It has 6 levels of adaptive measurement. So it's a block structure. You start with the coarse, yeah, so this is actually, the production code actually has adaptive mesh refinement. It's block structure. So you have a 0th level block of mesh, and then depending on certain criteria, you locally refine. But this is still quote unquote high fidelity, meaning the form of the equations that are being solved are assuming that there is no modeling required for subgrid scale. So there's no subgrid physics that can. You're just placing the mesh locally as the refinement dictates. But you could easily, in fact, this particular code group is envisioning doing multi-fidelity. And in fact, we propose using radiant detection as a criterion for switching between the different fidelity or turning on refinement locally. So when you know that something rare is happening somewhere locally, you might take some action. That could be switching to a high fidelity form of the equations or defining the mesh locally. So it's a proposal, but yeah, that's an idea.
Thanks.
So if I heard correctly, did you say there is no subgrid modeling in this code?
In this particular simulation, no.
Full DNS?
Full DNS.
That's it.
Yeah, and that's why, I mean, because these were all part of the Exascale project, they had a target that they had to run a simulation that would qualify as
Yeah, because typically, like using this AMREX framework, when we do the simulations, we limit like how many levels of refinement we
Yes.
can afford,
Yes,
because
I know. Yeah.
adaptive mesh refinement otherwise would try to go all the way up to.
Yeah, I know. With AMREX, turning on AMR levels beyond 2 or 3 is not for the faint hearted. Yes, and that's why I did want to point out that this simulation was a 6-level AMR. This was truly one of those hero simulations.
So we went all the way up to Kolmogorov scale? Or?
Yes. And again, for combustion, the Reynolds numbers allow you to do that. For atmospheric flow, the Reynolds
we mostly like we have the capability of doing DNS theoretically, but practically
you do
we limit to.
I think the Reynolds numbers in atmospheric flows are probably 2 or 3 orders of magnitude greater. So yeah, the requirement is